Hello everyone. Alright, today is part 2 of our vector video. So many of you are looking forward to this video as this is the part that really you encounter problem. In fact, vector traditionally there's two kind of questions. The first kind is the one where you have to do showing using a scalar and vector product. So your a dot b equals to b dot c, then you have to show the different expression. So today we're going to focus on the type 2, which is to solve the actual question involving lines and plane. So to start off with, we take a look at this equation of a line first. So there's many different forms, and you are also expected to know how to change from one to another. So as part of the video during the doing part, I will be doing some of the changes, but over here in the first two slides, what I really want to show is to remind you the equation of the line and the equation of the plane. So the very first one here is the equation of a line, which is r equals to a plus lambda b. So it's quite similar to your coordinate geometry. Remember coordinate geometry? Where you are actually talking about like, let me change the color of the pen first. Okay, I think in the last video, the color was a bit off also. So y equals to mx plus c, remember? So y equals mx plus c is for the m to give a direction and for the c to talk about a unique point that's specifically for the line itself. So for the equation of the line, it's the same as well for vector. You also need to use a direction, which is given by this d called the directional vector. And this a, which is a known point on the line itself. So with that, collectively, it will be like your y equals mx plus c. And the directional vector usually is the part that you get from the, points on the line. Why, right? Because we can actually use that to find the displacement vector. And as to what is displacement vector, you can take a look at my first video. The description is actually there. So what happens is that, right, you need to have a direction and you need to have a point. So do not be confused. The displacement vector is actually not the equation of the line. So like for instance, if there's an a here and there's a b here, let's say this is 1, 1, 2, this is 3, 1, 2. So I will say that if I find AB is 3, 1, 2 minus 1, 1, 2, then this will become 2, 0, 0. 2, 0, 0 is the vector AB, which is the displacement vector and the directional vector of this line. Yeah, but this is not the vector, the equation of the line they are looking for. The one they are looking for is that you have to take the a plus the lambda of the b. Lambda is a constant. So basically any point r, so this r that you see here, right? This r is in fact, any point on the line. Okay, any point on the line. So it can be given by a specific point plus a scalar multiple of the direction of the line itself. Okay, so this is the vector equation of the line. Next, the vector equation of a plane. So once again, there's also many different forms where there's the scalar product form, there's a column vector one, as well as there's a Cartesian form. So it's all written here as you can see here. So the first one is the column vector one, where you have the two directional vector which the plane is parallel to. So unlike the equation of the line where there's only one direction, but a plane is a 2D object. So you need to define it width-wise, length-wise, not height-wise. So these two directions. So as a result of that, you will have D1 and D2 as the two directional vector. And if you multiply the lambda and the mu, basically lambda and mu is just to represent some constant. Okay, some constants, lambda and the mu. Then after that, if you multiply to the directional vector plus a specific point on the plane, then collectively that will be the equation of the plane. So once again, the D1 and D2, like how I showed you in the lines case, is you have to pick any 2 points on the plane, you find the vector, then that will be the displacement vector, which gives you the direction as well. So a question usually will give you several points on the plane, then after that, right, they need you to use those points to work out the direction from there. Okay, then of course another way is that r dot n is equals to d. So the n here is what we call the normal vector to the plane. What normally we will do is that, right, the n is given by the directional vector 1 multiplied by the direction vector 2. So that will give you the normal vector to the plane itself. Yeah, so you cross the two directions. So if you're going to cross the two directional vector, okay, then this two directional vector will then be, the vector that you get will be perpendicular to D1 and D2. Okay, and of course, last but not least, the Cartesian form. The Cartesian form is really gotten from the scalar product form, because if I'm going to change my R to X, Y, Z, and then dot with a certain direction, the normal vector n equals to D, right? Then if let's say n is, for example, maybe instead of writing n, we write 1, 1, 2, and you do the dot product, you will get x plus y plus 2z equals to D. All right, so that's where you get your Cartesian form. So how to change between the forms, these are something that's quite basic. So maybe you can refer back to your own notes to take a look at that. Yeah, but basically the main thing I want to talk about here is really how to work on the problem. Okay, let's look at our first example for today's question. Imagine we have a point A and B. These are the position vector, with position vector I plus 2j minus k, 2i plus j plus 4k. So these are the 2 points of A and B. Yeah? Then after which, right, they say the line L has a Cartesian equation given by this. So most of the time, they don't need you to change, but they need you to change back to get to the thing that you really want. So A asks you to show that line AB and L intersect and find the position vector of their point of intersection. So basically, if we're going to draw a picture, right, of it, a diagram of it, it looks something like this. Okay, let me change back my color first to red color now. So imagine you have a, okay, sorry, this is not a plane, this is a line. Okay, so let's say you imagine you have a line. Okay, this line is called L. Then of course we have 2 points A and B, right? Okay, this is A, this is probably B. Okay, this line that passes through A and B, according to the question, will be intersecting L at a point. So let's call this point, let's say R maybe, all right? So in this case, they want you to show that they intersect and also at the same time to get this point of intersection. So all you need to do is that, right, you need to be able to do what we call a simultaneous equation. Right? It's quite similar to coordinate geometry. Do a simultaneous equation. So let's begin by finding the equation of the line that passes through A and B first. So we find the displacement vector AB is equals to, okay, OB is 2i plus j plus 4k, right? So this is 2, 1, 4. Then our OA will be 1, 2, minus 1. So this will give you 1 minus 1, 5, right? This is my AB. Then after that, we will be able to get the equation of the line. Okay, let's call this L2, okay, L2. So L2 equation will be R equals to the point A, which is 1, 2, minus 1, plus the lambda of 1 minus 1, 5. Okay, this is the equation of line L2. Okay, so L2 is this, and L, which is our first line, right? L is actually the other equation, which was given to you in the Cartesian form. So let's change it back to the column vector form first, because only when they are in the same form, then I can do the simultaneous equation. So what we will do is that, right, I will equate x minus 2 over 2 to be equals to mu. Okay, so what really happened here is that, right, this x minus 2 over 2, y minus 4, and z plus 5, right, is in fact everything is equals to mu. Okay, think of it that way. So then after that, I can make x a subject here. I'm going to get 2 plus 2 mu. Okay, let's do that for y as well. So y minus 4 equals to mu. So y will be equals to 4 plus mu. Then, of course, last but not least, z plus 5 is equals to mu. And z will be equals to negative 5 plus mu. Okay, so we are done. Then after that, the equation of the line L will then be R equals to 2 plus 2 mu, 4 plus mu, minus 5 plus mu. Okay, then we separate it, we will get 2, 4 minus 5, okay, plus mu, 2, 1, 1. Okay, that's the equation of line L. And in order to show that they will intersect, now let's begin the simultaneous equation solving. Okay, I'm going to write at the bottom. So equation of line L must be equation of line L2. So I'm going to equate the two of them together, but I'm not going to separate them. I'm going to put the thing together. So L will be 2 plus 2 mu, 4 plus mu, minus 5 plus mu, and this is equals to the equation of line L2, which is 1 plus lambda, 2 minus lambda, minus 1 plus 5 lambda. Okay, so something like that. Okay, then what will be the next step? Find your lambda and mu, which both sides will agree. So which means to say that you equate 2 plus 2 mu equals to 1 plus lambda. And then after that you take 4 plus mu equals to 2 minus lambda. Okay, in fact, you can also do the last one, which is minus 5 plus mu equals to minus 1 plus 5 lambda. Okay, so you just need to pick any of the two equations to do a simultaneous equation and find your lambda and mu. Okay, I'm going to skip that step and then I will get you a lambda now. So lambda, according to the thing that I have already solved, okay, lambda is actually equals to minus 1. Then mu is also equals to minus 1. Okay, then last but not least, right, you put this back into one of the equations and make sure left and right hand side are satisfied equal. So if I put it back into equation 1, 2 minus 2 is equal to 0. Then 1 minus 1 on the right side is also equal to 0. I'm looking at this one, by the way. So I let mu be minus 1 and lambda be minus 1 as well. Okay, and it's satisfied, so it's correct. Okay, so now I've proven that the lines are actually intersecting. And last but not least, let's find the point of intersection. Okay, for that, I'm going to write over here. Okay, let me squeeze it here. Okay, so the point of intersection will then be given by 2 plus 2 minus 1, 4 plus negative 1. Okay, 4 plus negative 1. And last but not least, minus 5 plus minus 1. So we will get, okay, let me write on top. We will get 0, 3, and minus 6. So this is the point of intersection. There's a real reason why they ask you to find A. So we're going to discover that in part B. Okay, so this is A. So I show the point intersect because we have a set of lambda and mu which both lines will satisfy. Point number 2 is that, right, I found the point of intersection. Okay, that is part A. So let's move on to part B now. So in part B, you are asked to find, there's this point N, and then after which, right, they ask you to show that AN is perpendicular to L. So how do we do that? Let's start by drawing out the, line first. So imagine this is line L. This is line L. So the equation is given by this. This is the equation of line L. Then after which, right, we have the line. Okay, we have a point that is N over here. Okay, this is N. So this N lies on the line L, where y is equal to 4. Then after which they want you to show that AN is perpendicular to L. So point A will be here. And point A, we know the coordinate itself. So this is 1, 2, minus 1. Okay, so to find whether this is actually perpendicular, right, we need to first find out what is N. Okay, what is N? So we're going to use the equation of the line L to find out whether to find out the N first. Okay, so from this equation, right, actually point N can be given by the equation let y be 4. So y be 4. And then after which, right, we will get x minus 2 over 2, which is equal to 0, right? Because when y is 4, 4 minus 4 is 0. Then we can actually solve for x. X will become 2. So you move the 2 over, then after that multiply the 2, then move the 2 over, then we will get x equals to 2. Then after which, we also equate z plus 5 to be equal to 0. So z will be equal to minus 5. So what exactly is ON? ON is then given by 2, 4, minus 5. Okay, so this one is the coordinate, coordinate and as well as the position vector of ON. Then from there, we're going to find AN now. Okay, so step 2 will be AN. So AN is given by ON minus OA. So 2, 4 minus 5, 2, 4 minus 5, minus away OA, which is 1, 2 minus 1. Then we will get 1, 2, okay, 1, 2 minus 5 plus 1 will be 4, right, minus 4. Okay, this will be our AN. Okay, this is our AN. And then after which we do a dot product. So let's do a dot product of between the directional vector of L as well as AN. So AN going to dot with the directional vector of L. So let's call it D. And the directional vector of L, okay, directional vector of L is in fact, okay, let me have a look. The directional vector of L, as previously we have determined, it is actually 2, 1, 1. Okay, so we're going to do 1, 2 minus 4 dot with 2, 1, 1. Then we will get 2, then plus 2 minus 4, which is equal to 0. So in fact, yes, AN dot with D is equal to 0. D is the directional vector of L. So in fact, this is shown to be, so AN is in fact perpendicular to L. Okay, we have shown it already. Okay, next, we need to find the equation of the image, of the line image, or reflection of AB into L. So just now in the previous part, we have done that already. There's a line L which passed through both point A and point B, right? Okay, and now they want us to find the reflection. Okay, let me draw a blue color thing here. So the blue color line is the reflection. And if you recall just now, we have already found the point intersection, isn't it? So the point intersection was given by 0, 3, minus 6. Okay, we're going to use that for this second part. And if I want to find the equation, okay, of the image by reflection about the line L, so what we need to do is that, right, we need to find A prime. Okay, we need to find, in fact, FA prime. Okay, we need to find FA prime. Because FA prime is the directional vector of the blue color line. Okay, and I also need a point that is on the blue color line, which I can use 0, 3, minus 6. So, which also means to say that if you continue from here, I'm going to use ratio theorem for this part. Okay, I'm going to copy this here. So, by ratio theorem, it looks something like that. Okay, this is point F, this is point A, this is A prime, and then if I draw a line here, this is N. N is the full perpendicular, and because it is a mirror image, so meaning to say that this will be 1 unit, this will be 1 unit, the length will be the same. Okay, so by ratio theorem, we can then say that Fn is equals to, okay, is equals to Fa, okay, plus Fa prime over 2. So this is by ratio theorem. And what we really want to find is Fa prime, which is equals to, okay, move the 2 over, you get 2 times Fn, right? So 2 times Fn, then you move the Fa over, it's a subtraction. Okay, then you will get this. And of course, prior to this step, actually you need to find your Fa first. Okay, and you should have already gotten the Fn. So if we have done it correctly, okay, now we move to the last part. So you will get 3, 3 minus 3. Okay, this is your Fa prime. But in this case, I just need a direction. Once again, you can actually take the simplest form of this. You take out the 3 first, then you get 1, 1 minus 1. So 1, 1 minus 1 will be the directional vector of the blue color line. Okay, and the final equation will just be R, which is equals to 0, 3 minus 6. This is a point which your image line will pass through, plus mu 1, 1 minus 1. So this will be the final answer. Okay, this is the final answer. So this directional vector was found by using ratio theorem to find your Fa prime. Then after which, the point which this line will pass through is F itself. And with that, you get the equation which is a mirror image about the line L. Okay, so this is the two-part question where part A, they ask you to find the point intersection, And if you notice, this was also being used in part B because I need to use the point F. Okay, I need to use the point F to find out what is my FA as well as my FN. Okay? Okay, let's move on to our last example here, which is the one that got to do with plane. So we have talked about the thing that do with line. Now let's move on to plane. Okay, so in this question, right, the start point was they gave you the vector equation of the plane, which contains A, B, and C, but actually they only give you A, B, and C. They didn't give you the plane equation. You are supposed to figure out yourself. And then after which, right, they want you to find the foot or perpendicular of F to pi. Okay, and this vector F that has a coordinate of 1, 1, 1. So let's try to understand the problem by first making a sketch first. So this is the plane. Okay, this is a plane. So this plane contains 3 points, point A, point B, and point C. So A is 3, 2, minus 1. Okay, let me rewrite this again. So sorry. So this is 3, 2, minus 1. B on the other hand is 1, 0, minus 1. And C is minus 1, 4, 0. And to find the foot of perpendicular, right, actually you will need the normal vector. Okay, later you will see why. So let's try to find the normal vector of this plane first. I don't need the column vector form of the plane, but I need the normal vector. So let's use the 2 point, or rather the 3 point given to you to find the directions. So we find AB first. AB is given by OB minus OA. So 1, 0, minus 1, minus away 3, 2, minus 1. So this will give us minus 2, and the last one is 0. Then AC, on the other hand, is given by OC, minus 1, 4, 0, minus OA, which is 3, 2, minus 1. Then this will give us minus 4, 2, and 1. Okay. Then last but not least, you do a vector product now. So the vector product is AB cross with AC. Okay, and then you work it out, you will get minus 2, 2, minus 12. Okay, I've done it previously, so I just write down that. Okay, so this is the vector product of AB and AC, which is the normal vector. Okay, the normal vector. But once again, for direction wise, I'm not going to use everything. If I factorize a minus 2 out, I will get 1, minus 1, and 6. Okay, I'm going to use this as my normal vector from here. Okay, and this will help me to find the foot of perpendicular from F to pi. Okay, let me use a new page to do this. Okay, so this is the plane, right? The normal vector is here, and previously found is 1, minus 1, 6. Okay, this is my normal vector. Okay, and point F, right, is here. Can be here 1, 1, 1. So this is my point F. Or OF vector is equals to 1, 1, 1. Okay, and they want you to find why I put directly on top and that's contained in the normal vector, right? It's because that I'm going to find the foot of perpendicular. So I need to drop down from F to the plane itself, right? So that's why I say that it is in the line, which is the normal vector. So this is our foot of perpendicular N. Okay, and by this point, you might notice that if I drop down from F to the plane, point N is in fact, okay, it must be a line that is perpendicular to the plane. Okay, a line that's perpendicular to the plane. And if that's the case, you have to use the scalar product form because they will be perpendicular. So let's try to find the equation of the line that pass through F and N now. So the line will be, you're going to use the directional vector as 1, minus 1, 6. Okay, so the equation of line, let's call it L, would have been 1, 1, 1, okay, plus the lambda of 1, minus 1, 6. Okay, and in order to determine the point N, I'm going to do a simultaneous equation now. So now I will need to find out the scalar product form of the equation of the plane first. Okay, so which I call it pi. So pi will be, okay, wait, this one is supposed to be R, sorry. So this will be R dot with 1, minus 1, 6. Then the right side is a dot n, so I have to pick a point. Let's say I use 1, 0, minus 1 on the plane, dot with 1, minus 1, 6. Then I will be getting 1, minus 6, so will be minus 5. Okay, r dot 1 minus 1, 6 is equal to minus 5. Last but not least, to find the full perpendicular, which is the intersection point between the line and the plane, right? I'm going to substitute this inside here. So this is how it will look like. 1 plus lambda, 1 minus lambda, and 1 plus 6 lambda, dot with 1 minus 1, 6 is equals to minus 5. So 1 plus lambda, minus 1 plus lambda, and plus 6 plus 36 lambda will be equals to minus 5. So if you continue to solve this, actually you will get lambda to be equals to negative 11 over 38. So also previously I already solved it. Yeah, lambda equals to minus 11 over 38. Then after which, right, now you put your lambda back into the equation of the line, because this point n, point n is actually in the line. So we can actually put this specific variable lambda to find the point n, which is on the line L. So now finally I will say that ON, okay, ON is equal to what? Is equals to 1, 1, 1, okay, plus negative 11 over 38, okay, then 1 minus 1, 6, okay, then you solve for it. ON itself will really just be 27 over 38, 49 over 38, minus 14 over 19, okay, which I will do this, I will take out the 38, right? So 1 over 38, 27, 49, and negative 28. Okay, why I usually do this, because you can see if you're going to put all the fraction inside the bracket, somehow it's going to be very cluttered. So it's better to take out the denominator out of it. Then this will be easier to see. Okay, and that will be the last example for today. You can see that actually in the vector kind of question, when I record this, it's also easily a 10-20 minute kind of video because the question is really very long. And in fact, you're going to use everything that you have learned from the start about how to find the scalar product, how to find the vector product, and how to find full perpendicular. So when you're doing your revision, maybe you want to make a collection of the things that you're expected to know, how to find the full perpendicular, how to prove that the two vectors are perpendicular to each other using the dot product, how to find angle, how to find area. So you make a list of all these things first, and best is that you need to understand the equation that you're going to use and what are the things that you need to put inside. Okay, so these are all the things that you need to learn before you can even do a question like that. So once you are at it, you cannot be referring back to your notes again. Hey, what formula is this? What formula is that? Then that's not the case. Okay, you will be struggling in the question one. So it's better to make sure you iron out all the details of all the steps that you need to do to find like this, find that, scalar product, vector product, and all these things. So make sure you're very familiar before you dive into a question like that. Okay, I hope you liked today's video. This is Vector 2, basically to show you in real life how an example of this kind of question will be done. I'm quite sure you have watched your teacher's video recording as well, but this is actually going into the detail of the steps. So run through the video again, look at the steps I do, and try to emulate and think about why I do certain steps. Okay, and if you are not sure, please feel free to comment, subscribe and like my video. And in any case, I'll be moving on to also talking about another topic which will be on the calculus, differentiation and integration. So that will be my next video. So if you need help in that, please stay tuned and look out for my next video. Okay, thank you very much for today. I will see you in the next video.